All right, so get this. We're diving deep into Amazon Aurora today. It's this relational database that's kind of causing a stir because it's built specifically for the cloud. We've got some serious research papers and even a blog post straight from the AWS team to unpack. So let's jump right in.
Yeah. You know what's fascinating about Aurora is how it tackles those age-old database headaches, like keeping your data safe when things go wrong and making sure everything runs smoothly, even when you've got tons of users hitting it all the time.
Exactly. Imagine you're running a huge online store. What happens if your database crashes? You're losing orders, customers are frustrated. It's a disaster. Aurora promises to solve this, so let's get into how they do it.
Well, they start by rethinking durability. Traditional databases often rely on a simple majority vote to keep data safe. Think of it like a school election. Whoever gets the most votes wins.
Okay, that makes sense.
But what if a bunch of voters suddenly disappear? The election results might not be reliable anymore. The same thing can happen with a database if an entire availability zone or AZ goes down. It's like losing a huge chunk of votes.
So an AZ is like a location for your data, right? And if it goes offline, a big part of your database goes with it.
Exactly. That's where Aurora's 643 quorum model comes in. Instead of a simple majority, they replicate your data 6 times across 3 AZs. For any change to the database, 4 out of those 6 copies need to agree, and to read the data, you only need 3. This means it can handle an AZ outage plus another failure without missing a beat.
So even if a whole region goes dark, my online store can keep taking orders. That's a game changer.
Absolutely. It's all about minimizing downtime and keeping your applications running smoothly.
But wouldn't all this replication make storage ridiculously expensive? It sounds like you're storing 6 times the data.
That's where Aurora gets clever with segmented storage. Instead of copying the whole database 6 times, they break it down into smaller 10 GB chunks. So each chunk gets replicated, but it's way more manageable.
Ah, so it's like splitting a giant pizza into individual slices. Easier to handle, and you can still share with everyone.
Exactly. And this also makes recovering from a failure lightning fast. They've actually tested this. The 10 GB segment can be repaired in just 10 seconds on a fast network.
Wow, that's like fixing a tiny scratch on your car instead of replacing the whole engine. Now, the next thing that caught my eye was this idea of the log is the database. I have to admit, that sounded a bit cryptic at first.
It's a pretty radical shift in thinking. Traditional databases write a lot of data to storage, actual data pages. Log records extra copies for safety. It's a recipe for slowdowns.
Okay, so it's like trying to move a whole library book by book instead of just copying the information you need.
I like that. Aurora simplifies things by treating the log as the primary source of truth. They only write redo logs to storage, and the actual data pages are generated on demand. Think of it like having a blueprint. You only build the house when you need it.
This makes sense to me, but why is it so much faster?
Well, think of it this way. Traditional databases are constantly writing tons of data back and forth, creating traffic jams. Aurora streamlines this by writing only essential log information, making it much more efficient.
So it's like taking the express lane on the data highway.
Ah, that's a great way to put it. And they have the data to back this up. In one test, Aurora handled 35 times more transactions than a traditional mirrored MySQL setup, while doing way fewer operations per transaction.
Wow, that's a serious performance boost. But we're talking about a lot of moving parts here. What happens if, despite all this fancy footwork, something still goes wrong?
That's where things get really interesting. Traditional databases have this long, tedious process of replaying the entire log to recover from a crash. Aurora, however, uses what they call asynchronous magic to speed things up.
Hold on, asynchronous magic. I feel like I need a wizard's hat to understand this.
It might sound like magic, but it's actually a very clever approach. Instead of waiting for every single operation to finish before moving on, Aurora constantly tracks and advances points of consistency and durability. It's like sending an email you hit send and move on while the email system takes care of delivery in the background.
Ah, so it's not waiting for everything to line up perfectly before taking the next step. It just keeps things moving, even if some pieces are still in transit.
That's the gist of it. This asynchronous magic means that even after a crash, Aurora can recover incredibly quickly. We're talking under 10 seconds, even with massive amounts of data.
Okay, I'm starting to see why people are excited about this. It's like having a database with a built-in self-healing superpower.
Yeah.
But there's still more to uncover, right? This blog post mentions something called Amazon Aurora DSQL, which sounds even more futuristic.
Now we're getting into the realm of serverless and distributed databases. D-School takes all these amazing features we've talked about and applies them to a database that can span multiple regions and scale almost infinitely.
Okay, now you're really piquing my curiosity. I can't wait to dive into that. But before we do, let's take a quick pause and recap what we've learned so far about Amazon Aurora.
Sounds good. We've covered how Aurora tackles durability with a clever quorum model and segmented storage. We've seen how it redefines efficiency by treating the log as the database and using asynchronous processing to streamline operations. And we've touched on its incredible recovery capabilities, all thanks to this asynchronous magic.
It's a lot to take in, but it's clear that Amazon Aurora is not just another database. It's a fundamental rethinking of how relational databases work in the cloud.
Absolutely. It's designed for a world where high availability, scalability, and efficiency are paramount.
And now we're ready to explore how Aurora Diesel takes these concepts to the next level. But that's a story for part 2 of our deep dive.
All right, welcome back to our deep dive into Amazon Aurora. Last time we talked about how Aurora reimagines data durability and efficiency with some pretty clever tricks. Now we're going to explore how it handles crash recovery and those tricky situations where things don't go quite as planned. Yeah, you're right. We can't just assume everything will always run perfectly. Things break, networks hiccup, and sometimes entire data centers have issues. Aurora's ability to recover quickly and gracefully from these disruptions is a major part of its appeal.
Okay, so let's revisit that asynchronous magic you mentioned earlier. It sounds like it plays a key role in how Aurora recovers from a crash. But honestly, I'm still a little fuzzy on how it actually works.
I hear you. It's one of those concepts that sounds abstract until you see how it all fits together. Remember how Aurora only writes redo logs to storage? Well, each of those log records gets a unique ID, like a timestamp called a log sequence number, or LSN. These LSNs are ordered so Aurora can track the progress of operations without needing constant communication between different parts of the system.
So it's like having a perfectly synchronized dance routine, even though the dancers are all in different rooms?
That's a great analogy. Each dancer knows their steps and when to perform them based on the music, even if they can't see each other. Similarly, Aurora uses LSNs to coordinate operations efficiently. Now the database keeps track of the highest LSN, where it knows all previous log records are safely stored. This is called the Volume Complete LSN, or VCL.
So the VCL is like a checkpoint. Anything below that line is good to go.
Exactly. If the database crashes, it just needs to find that VCL and pick up where it left off. No need to rewind and replay the entire log, which can take forever with traditional databases.
That makes sense. But what about all these operations that were happening right when the crash occurred? Some might have finished, others might need to be undone. How does Aurora deal with that mess?
That's where Aurora's storage service steps in. During recovery, it figures out the highest LSN where it can guarantee all previous log records are available. Anything beyond that gets truncated, like hitting the undo button on any incomplete actions.
So even if the storage has some extra data, it knows to ignore it and stick to a consistent point in time.
Precisely. To make this even more robust, Aurora uses consistency point LSNs, or CPLs, as additional checkpoints within the log. Think of them like safety nets, ensuring the database always lands on a stable state.
Okay, so this asynchronous approach not only makes recovery super fast, but also keeps the data consistent. It's starting to feel like Aurora has thought of everything.
They've definitely put a lot of thought into it. But we're not done yet. Let's talk about reads. You might think a system focused on durability would always need to check multiple copies of the data for every read.
Right, to make sure you're getting the most up-to-date information.
Exactly. But Aurora has another trick up its sleeve. Remember the VCL? Well, the database also knows which specific storage segments have the latest version of each data block.
So it can just go directly to the source, no need to ask for directions.
Exactly. This makes reads lightning fast. But of course, for high-traffic applications, you often need read replicas to handle all those requests.
Ah, so it's like having multiple copies of a popular book at the library so more people can check it out.
That's a great analogy. Now, you might think managing consistency with all these replicas would be a nightmare. But Aurora uses a shared storage approach. All the replicas connect to the same storage volume as the primary writer instance.
So it's like everyone is working from the same master document, no need to worry about conflicting versions.
Precisely. Replicas receive a stream of updates and can also read directly from the shared storage. This makes them super quick to set up and tear down without copying the entire database. Plus, adding replicas doesn't affect the durability of the system.
Okay, this is making a lot of sense now, but there's one thing that's still bugging me. If these replicas are getting asynchronous updates, how do we know everything stays in sync structurally? I mean, databases have all sorts of complex structures, like indexes and B trees, right?
That's a great question. Aurora ensures that updates to these structures are applied atomically, meaning they're either fully completed or not done at all. Think of it like rearranging furniture in a room you don't want to be left with a half-assembled bookshelf.
So even if a replica is slightly behind, it will always see a complete picture. No broken furniture.
Exactly. And to make sure all read replicas are seeing the same consistent view, Aurora uses special control records that act like bookmarks. It's like everyone agreeing to read from the same page in the book, even if they're reading at different speeds.
This is so cool. It's like a perfectly choreographed dance with all these asynchronous operations working together seamlessly.
That's a great way to put it.
Yeah.
But there's one more piece to this puzzle we need to address. How Aurora handles failures and changes in those groups of storage segments we talked about earlier, the quorum set.
Yeah, you're really testing my memory. Quorum set's right. That was the 643 thing for durability.
You got it. But those sets aren't static. What happens if a segment in a quorum set fails or you need to add more storage? Aurora needs a way to manage these changes without disrupting operations.
I can see how that could get messy if not handled carefully.
Absolutely. Imagine you're trying to replace a tire on a moving car. You need to do it smoothly and safely. Aurora uses a similar approach. Let's say you have a quorum set with 6 segments, and one of them starts acting up. Instead of directly swapping it out, Aurora first adds a new healthy segment to the set.
So it's like having a spare tire ready to go before you even remove the flat one?
Precisely. This creates an expanded quorum set, and Aurora uses something called an epoch, which is just a fancy way of tracking changes to the set. If the old segment recovers, we can simply revert to the previous epoch and remove the new segment. But if the old segment stays down, we transition to a new epoch with the new segment permanently in place.
So it's like having a built-in safety net for managing these changes. No sudden jolts, just smooth transitions.
Exactly. This approach allows Aurora to handle changes without blocking reads or writes. And every step is reversible to prevent data loss and minimize downtime.
Wow, they really thought of everything, didn't they? But it seems like all this replication and redundancy would get expensive. Isn't there a way to optimize costs without sacrificing durability?
There is. Aurora introduces the concept of unlike members in a quorum set. Instead of assuming all members are identical, you can have different tiers of storage. For example, a quorum set might have 3 full segments that store both log records and data, and 3 tail segments that only store log records.
So it's like having different levels of membership at a club. Some members have full access, others have limited privileges but are still part of the group.
That's a great way to visualize it. This reduces storage costs because you're only fully replicating the data 3 times instead of 6. You can even combine different storage types like fast SSDs for frequently accessed data and slower HDDs for archival data.
It's like having a toolbox full of different tools and knowing exactly which one to use for each job. This is seriously impressive stuff. It's clear that Aurora is pushing the boundaries of what's possible with relational databases in the cloud.
Absolutely. And all this is built on the foundation of treating the log as the database offloading processing to the storage layer and embracing asynchronous operations. It's a paradigm shift that's transforming the way we think about data.
This has been incredibly insightful, but I have to admit my brain is starting to feel a bit overloaded. All these technical details, quorum sets, epochs, LSNs, it's a lot to process.
I hear you. It's like learning a new language. It takes time and effort to understand the nuances. But the key takeaway here is that all these seemingly complex features translate into real-world benefits for anyone building and using applications that rely on relational databases.
Right, it's not just about the technical wizardry, it's about how it actually makes a difference for users and businesses.
Exactly. We're talking about faster response times, increased scalability, reduced downtime, and lower costs. Those are benefits everyone can appreciate.
Absolutely. It's not just about immediate gains, but also the possibilities that open up when you have a database that can seamlessly scale, adapt to failures, and evolve with your needs. But we still haven't talked about how Aurora DSilk takes all of this to the next level with serverless and distributed features. That's a story for part 3 of our deep dive.
I agree. We've only just scratched the surface of what Aurora can do. DSQL is a whole other world of innovation, and I can't wait to explore it with you.
Welcome back to the deep dive. We've been unpacking Amazon Aurora, exploring its innovative approach to durability efficiency and crash recovery. Now let's kind of shift gears and talk about Aurora DSQL. It's the serverless and distributed version that takes these concepts to a whole new level.
Yeah, DLWIL is really exciting because it builds upon the same foundational principles we've been discussing. Redo logs, asynchronous processing quorum sets. It extends these ideas to create a database that's not just highly available, but incredibly scalable and easy to manage.
So the blog post mentioned that DSQL offers two main configurations, single region and multi-region. Let's start with single region. How does that work?
Okay, so imagine you have a DSQL cluster set up in a single AWS region. In this setup, DSQL is active across three availability zones. This means each AZ has a complete copy of the data and can handle both reads and writes.
So it's like having three separate branches of a company, each capable of operating independently.
That's a great analogy. This eliminates the need for traditional failover processes, which can be time-consuming and disruptive. Plus, because write transactions are committed to a distributed log that's replicated across all three AZs, you get strong data consistency, even if something goes wrong.
So no matter which AZ my application connects to, it's always getting the most up-to-date data. That sounds incredibly reliable.
That is. And here's the best part. If an entire AZ goes down, DSQL automatically routes requests to the healthy infrastructure without any human intervention. It's like having a self-healing system that takes care of itself.
That's a huge relief for anyone running mission-critical applications. But what about those rare events where an entire region experiences an outage? That's where multi-region DSQL comes into play, right?
Exactly. Multi-region clusters take resilience to the next level by creating two linked clusters in different AWS regions. Each cluster has its own endpoint for reading and writing data.
So it's like having a mirrored backup in a different part of the world, constantly staying in sync with your primary database.
That's a great way to think about it. And because writes are synchronously replicated across these linked regions, you get strong data consistency across both locations. You can read or write from either endpoint and always see the same up-to-date data.
Okay, so this multi-region setup sounds like the ultimate safety net. But I have to ask, wouldn't synchronizing data across such vast distances introduce some lag?
There's inevitably some overhead, but DSQL is designed to minimize it. It uses techniques like strong snapshot isolation and optimistic concurrency control to ensure smooth and efficient operation, even with multi-region replication.
So it's like having two musicians playing in perfect harmony, even though they're miles apart? Impressive.
And to further enhance data integrity, DSQL uses a third region as a witness. This region doesn't host a cluster, but it keeps a record of recent transactions to help resolve any conflicts that might arise during a major outage.
So it's like having an impartial judge who can step in and settle any disputes between the two primary regions. That's a clever way to ensure consistency, even in the most extreme scenarios.
Absolutely. It's a testament to how much thought and engineering went into making DSQL the ultimate solution for applications that demand the highest levels of resilience.
So it's clear that DSQL takes availability and durability seriously. But what about scalability? Can it handle massive amounts of data and traffic?
Oh yeah, DSQL was designed for practically unlimited scale. It adapts to workloads of any size. And its various components like query processing, commit handling, and storage can all scale independently.
Mhm.
You don't need to worry about manually sharding your database or provisioning extra resources as your application grows.
So it's like having a database that can expand infinitely, like a magical bag that always has room for more.
That's a fun way to picture it. And because it's serverless, all the scaling happens automatically behind the scenes. You can focus on building your application without getting bogged down in infrastructure management.
That's the beauty of serverless, right? It just takes care of itself. But with all this data spread across multiple regions, security must be a top concern. How does DSQL address that?
Well, DSQL uses a multi-layered approach to security. It provides easy-to-use controls for data privacy and integrates seamlessly with AWS's identity and access management systems like IAM. It even supports token-based authentication, which is much more secure than relying on passwords.
So it's like having a database with a built-in security system that's always on guard.
Exactly. You can rest assured that your data is protected no matter where it resides in the cloud.
So we've covered a lot of ground today, from Aurora's innovative approach to durability and recovery to DSQL's incredible resilience and scalability. I have to say, I'm thoroughly impressed.
Yeah, it's amazing to see how Amazon is pushing the boundaries of what's possible with databases. It's inspiring to think about all the incredible applications these innovations will enable.
Absolutely. This deep dive has given me a whole new perspective on the future of data management. It's clear that Amazon Aurora, and especially DSQL, are leading the charge toward a world where data is no longer a bottleneck, but a powerful driver of innovation.
I couldn't agree more. It's an exciting time to be working with data, and Aurora is at the forefront of this revolution.
And that concludes our deep dive into Amazon Aurora. We hope you've enjoyed this journey into the world of cloud-native serverless databases. We'll be back next week with another fascinating topic and another stack of insightful sources. Until then, keep learning, keep exploring, and keep diving deep.